Hi, I'm Dr. Xu. Today we are going to talk about Tarjan algorithm and DFS, depth first search. So first of all, let's see what is DFS. So let's see this graph. This is a tree. We can see lots of directed edges in this tree. And how do we traverse this tree? Is using this method. This is so-called depth first search. We go from the root until we reach a leaf and go back to its parent and continue the same process until we see a leaf and go back. This is so-called DFS transversal. In this graph, let's define three edges, back edges, and the forward edge. Let's look at this. This blue edge is called back edge because this edge is from a descendant to its ancestor. So it's a back edge. The yellow one is a cross edge because none of the two vertex are the other vertex ancestor or descendant. This one is forward edge. One point is that during the DFS transversal, those edges should not be explored. But sometimes during the process, we will do some computing work. But the DFS tree doesn't contain those edges. All right, let's see the Tarjan's algorithm. Okay. Tarjan is a computer scientist in Stanford, and he found the following algorithm to find all the connected component, strongly connected component in a directed graph. He published the paper in 1971. And let's see the first picture. It's very interesting because you see two numbers. Actually, the first number is the number that a vertex is discovered or visited the first time. So all the vertices are numbered from 1 to n, and it's the total number of vertices. And the second number denotes actually so far the smallest number from one vertex to another that it can reach. It's a very subtle. It's actually in the code. You'll see the definition of the second number will be the minimum in its SCC or strongly connected component. So before we go to the code, let's see this. This is in this graph, we have actually 4 strongly connected components. This is the first one, second one, third one, and fourth. You see, actually, they don't have any 2 SCC or strongly connected component. You cannot travel from one to another and come back. Or if in this graph, if we consider each SCC as a point, then we get a new graph. In a new graph, there's no non-trivial SCC anymore. Trivial means the SCC is just one point. If yes, then we will see SCC should be combined. 2 SCC in this graph should be combined, and it should be larger. So now let's go to the code and see the problem in Tarjan's algorithm. This is the C++ code I modified to standard C++ 11. Let's see from the high level to lower level. So we are going to test several cases, but essentially, this is the function called SCC. What it does is that it will call SCC util function, and actually from line 39 to 41, this function SCC util will call on each tree in the graph. So where is the DFS? The DFS is here. DFS, actually SCC util, this function will be the DFS. It's a member function of the graph class, but what it does is DFS. Now how it works like this. First, it will start with a point, and you see this vector DICU. It is a vector. It will number the vertex such that the vertex will be numbered the first time it is discovered. And we use another vector low here to record the minimum number from a vertex that it can reach so far. So where is the DFS? Here is the DFS. You see this loop. Basically, when we look at the adjacent vertices from vertex U, then if it's not discovered, if V is not discovered, we call the, you see, we call the function itself. This is DFS, and the low value for U is equal to the minimum low level of U and the low level of V. What if the point is discovered already? Here is the subtle thing. If it is discovered and it's already in the stack, by the way, we should define a stack as T. And we use a vector to denote if a member is out of stack or in the stack. Using the vector is called stack member. Then here, the subtle thing is traditionally, there are lots of arguments about this actually. The traditional Tarjan's algorithm here use the line 95. And there are some arguments on internet that line 97 should work as well. So we are going to show either one works. So what happens during the DFS is that once during the DFS process, once it finds low U equals discover U, or the index the index of the vertex is equal to its low value, then it will stop. And pop up all the vertex after it, and pop up itself as well, and mark the stack member at that point to be false. So you will see the process is dynamic. Let's go back to the graph. Why those two methods are the same to update the low value? That's because you see during the DFS process, and if you remember the code, the stack will pop all the members if the members are in one SCC. So pretty much those FCCs, they don't affect, their low values don't affect each other, because sometimes when during the DFS process, when it's found a SCC, and the SCC, the whole FCC will pop out. That's how it works. Now you will see, using the two methods to updating the low value, essentially it doesn't affect the behavior, because when it's this the block code to pop stack members are only when we find the discovered number is equal to its low number. The two methods I mentioned doesn't affect if the discovered number equal to its low value. So that's why the two methods are equivalent. This is roughly the idea. The details involves more theorems or lemmas. So actually, so DFS is a really powerful tool for the research in graph theory. Thank you very much.